Welcome back. In the previous lecture, we talked about how we could use models to become clearer thinkers. In this lecture, what we're going to do is we're going to talk about how we can use models with data. And this is an important reason why people use models. In fact, when you talk to scientists about why they use models, whether they're social scientists or natural scientists, what they'll typically say is, well, we use models to take them to data, to basically use and understand data in better ways. Well, what I want to do is I want to unpack that in several directions. I want to give some specific reasons or ways in which people use models with data. All right. So the first real reason is just to understand some basic patterns in the data. So what do I mean? Well, you could look at data and it could just be a straight line and nothing could change. So for example, if you look at a system and ask how much energy is in the system, we know that energy is neither lost nor gained, so energy is a constant. And we can have a model that explains why we see, energy being a constant. Alternatively, you could see something that's just a straight line, that's just an increasing line. On a model that explains that. Now remember, we also talked about how we can see patterns in data, right? So we could see things that go up and down slowly like this, like business cycles, and we could have models that tell us why we see these sort of cyclic curves. We could have something that's much more spiky. We could have a model that explains that. So again, we talked about how there's this sort of hairball or this fire hose of data. There's tons of data out there. That data is going to have patterns to it, and what we can do is use models to understand why we see those particular patterns. Okay. In addition to the patterns, there's also just the use of models to predict specific points. So suppose you're out looking for a house and you see this house that's for sale and you're wondering, well, I wonder how much that house is going to cost. Well, you could have a model that says, okay, the price of a house depends on its size. So here's sort of the size of the house in square feet, and here's the price. We'll just put dollars in there for price. And maybe you've got a linear model. And your linear model says basically for every, additional square foot, the price of the house goes up $100 or $200 or something like that. Well, then if this is your model, it's a linear model, and you've got a house that's got this many square feet, say it's 2,000 square feet, right? And you go up here and find the point. If it's $100 per square foot, then your model would predict that the house is $200,000. So we can use a simple model to make some sort of prediction about just in the ballpark how much the particular house would cost. So this is, again, a common use of models. You construct a model, and from that model, you predict a point value. Okay, third reason why we use models is not so much to predict points, but to produce bounds. So suppose you're the economic advisor to the president, not a job you necessarily want, but suppose you are, and the president comes to you and says, what's inflation going to be next year or next month? Well, inflation doesn't move that quickly, and you might be able to say to the president, well, I think it's going to be 1.2%. And you might be pretty confident that it's 1.2%. But suppose the president says to you, I'm just in some long-range forecasts, so what's inflation going to be 10 years from now? Well, who knows what inflation is going to be 10 years from now? So you may have some fairly sophisticated models, but they're not going to give you a point estimate. So instead, what they might say is, well, I can tell you with pretty high probability that it's going to be between 0 and 3%. So it gives you a range, right? So your model won't tell you necessarily exactly what's going to happen because there's too many contingencies out there. There's too much complexity, too much uncertainty. You can't say for sure, but your model might give you some bounds about what's going to happen, and that can be really useful for making policy decisions. Okay, reason 4, retrodiction. What do I mean by that? Well, you can use models with data to predict the past. Now, there's a couple reasons you might do this. One reason is you might not have data from the past. So you might want to sort of use models to try and figure out what do we think the past was like. And this is things, geologists do this, biologists do this, anthropologists do this, archaeologists do this. They use models and data to try and figure out what do we think, temperature was like, how many animals do you think there were, what were these civilizations like, those sorts of things. If you have the data, then you can use models to see how good they are. So you can actually retrodict data to see if, in fact, your model would have worked. Let me explain what I mean. So suppose we're looking at some data stream. Perhaps let's stick with unemployment. Suppose the unemployment data looks like this for some period of time, right? And now what you're doing is you're saying, okay, we've got a model. We're going to ask how well that model would do. So what you do is you sort of fix that. You give that model data up to here, so it's fitting pretty well. And then at this point right here, you say, okay, let's see how well our model would predict from there on out. Well, maybe if you run your model, it sort of goes like this. Well, if it goes like that, you can say, our model in the past, if we had used the same model in the past, it wouldn't have worked. And so that makes you fairly dubious about whether the model is going to work now. So retrodiction, going back and testing past data, is a good way to test how good your model really works. Fifth reason, predicting other stuff. So you might construct a model for one reason. Let's suppose you're really interested in the unemployment rate. You construct a model to predict the unemployment rate, but out of that pops out the inflation rate. So you get something else. This is a good way to tell, how strong your model is, because typically you construct a model for one reason, it gives you other stuff. Now there's another type type of predicting other that's really cool about models. So when they developed the first models of the solar system, right, the heliocentric model, the sun in the center, right, so you've got the sun sitting here in the center and the planets orbiting, the math didn't quite work out right. And they figured out, there must be some big planet out here that's causing the orbits of the other planets to be skewed a little bit. And that big planet was Neptune. They couldn't see it, but their model predicted it. So their model predicted something else, something other, that it was evident in the data. So models can predict stuff other than what you expect them to predict, which is pretty cool. All right. Sixth reason, to inform data collection. So let's suppose that you're interested in educational reform, which is something I'm really interested in. You want to think, okay, how do we make better schools? Well, what you can do, remember in our last lecture about being a clear, better thinker, one thing models force us to do is name the parts. So if I want to think, how do we make better schools? Well, there's a lot of data out there on school performance. So what I want is I want some sort of model that explains why students do poorly and students do well. So I think, what are the parts of that model? Well, there might be things like teacher quality. We'll call that TQ, right? There might be parental status. We'll call that PS, like whether your parents went to college, whether they've got high school degrees, whether they're doctors, lawyers, that sort of thing. There might be total spending in the school district. That might matter, right? Things like class size. We just put CS for class size, but class size probably matters a lot, right? You might argue that, technology matters. Is there technology in the classroom? You might even argue, does general health, is health a big consideration? And you could even, argue, what is sort of what are the other students like in the school, right? Are there sort of peer effects? Does that affect how well students do? So if you don't have a model, you don't even know what data to go get. And so what models help you do is figure out, okay, what data should we get and what data should we include what data should we go out there and try and find in order to figure out how the world's going to work. So the use of models to name the parts is incredibly helpful for gathering data because it tells you which data to go get. Our last two reasons for why you model are a little bit different, but they're similar to one another. And that is that we can use data, right, to sort of tell us more about the model, and then we can use the model to tell us more about the world. So let me explain what I mean a little bit. It's kind of confusing. So one thing we can use models for is to estimate hidden parameters in the model. So here's a sort of a classic model from disease, from epidemiology, the study of disease. It's called the SIR model. So there's three types of people. There's susceptible people, there's infected people, and there's recovered people. So if there's a disease, you could be susceptible to it, you could be infected, or you could be recovered. And when you're recovered, then you're immune. You think you're not going to get it again. So let's suppose that you work for the Center for Disease Control, and suddenly you see, oh my gosh, people are getting sick. But you don't know there's some sort of flu going on, but you're not quite sure how this is spreading. Is it airborne, right? Is this virus spreading, through mucus or something? You're not sure. And you're also not sure how virulent it is, so you're not sure how many people are going to get the disease. What you've got, let's draw a little graph where you've got time on this axis, and you've got the number of people who have the disease. And what you can do is you can sort of see over time exactly how many people are getting the disease. Well, if you can see over time how many are getting it from that data, you can predict how virulent the disease is, like how likely it is to pass from one person to the other. And that's going to allow you to figure out, is the disease going to go like this, or is it going to go like that? And so from that data, you can estimate hidden parameters, right? Namely, how virulent the disease is. Like you can't tell by looking at data how likely one person is to get it from another. You can't tell by looking at the world, but by looking at how many people get it, you can go back and estimate that parameter. You can figure it out. That's what's really cool, all right? Last reason, calibration. So calibration refers to sort of constructing a model and then calibrating it as close as possible to the real world. Let me give an example here. So suppose I want to write a model of forest fires. So I'm going to draw some really bad trees here. Here's a tree. Here's another tree, right? And I want to know, what's the probability? These are horrible trees. Okay, what's the probability that the fire moves, right, from this tree to this tree? How fast does it move? All that sort of stuff. Well, what I could do is I could gather, and this data exists, tons and tons of data about past forest fires. And with that past data, I could calibrate a really accurate model of forest fires. How likely are they spread? How, their speed of spread depends on how dry the trees are, how much precipitation there's been, what the wind speed is, all that sort of stuff. Once I've got all that data, that would allow me then to figure out, how dangerous are particular forests, right? Because I could say, oh my gosh, northern New Mexico hasn't been rained in 2 years. Here's how dry the soil is. Here's how dry the trees are. Here's, how many acres of forest we have. Here's what the wind speed is. And you could know exactly how dangerous a particular forest happens to be at a particular moment in time. So you use all sorts of past data to calibrate a particular model, and your big model, and then you can use that model to construct policy. And that's what we're going to talk about in the next lecture, right? How do we use models to make decisions, to strategize, right, and to design things? Thank you.